Alrighty, in this video we're going to wrap up section P3, Polynomials and Special Products. This is just the second day on this, and we just got a couple of loose ends to tie up here. And I'm actually going to take this a step farther than what we see in the textbook. In the textbook, we do up to the cube of a binomial. If we have some quantity u plus v or u minus v raised to the third power, we have this little formula that you can memorize to expand that binomial. And actually, this is just a small piece of a bigger picture. It's called Binomial Theorem. And we're going to expand, I used x plus y instead of u and v, to any power of n. That could be to the 10th power. We could write it out, x plus y, that quantity, times itself 10 times, and do a whole bunch of, foiling and distributing that out to get the answer, a bunch of collecting like terms. But if we use this idea of a binomial theorem, we can do that sort of like with a shortcut. And if we look here at the formula here for the cube of a binomial, we have some coefficients. And in here it's, it's 1, 3, 3, 1, 1, 3, 3, 1, and we got some minuses spread out there depending on the signs. And where do those threes come from is, we can get them from Pascal's triangle, if you ever heard of that. So we start out here by putting a 1 and another one down here and a 1 down here. These are like little arrows. We just brought that one down. And this would be the coefficients for x plus y to the first. Since it's first power, we could drop the parentheses. The 1 is in front of the x and the 1 is in front of the y. So let's continue the pattern. I'm going to bring this one down, and I'm going to bring this one down. And the middle term, I'm going to add these together. 1 plus 1 is 2. And that would be x plus y, that quantity squared. I'm going to write it under here, and then I'll erase it. But if I FOILed that out, I would have x squared plus 2xy plus y squared. And the coefficients are 1, 2, 1. Let's continue with the triangle. Bring down your edges. Those ones just always come down. And now 1 plus 2 is 3, and 2 plus 1 is 3. Those are the coefficients for the expansion of x plus y to the third power. And don't get into the habit, you think, oh, that's a 2, that goes there, that's a 3, no, that's not how it's going to work after this level of the triangle. And I'll just bring over here, this is the right out of the textbook. The 1 is the coefficient for u to the first, the 3 goes here, the other 3 goes here, and the 1 goes to the v to the third. And that's as far as our book takes it, and we'll go one more step. I'm going to bring down my edges, my 1's again, and then I have 1 plus 3 is 4, 3 plus 3 is 6, and 3 plus 1 again is a 4. Those would be the coefficients if I was to expand out x plus y to the fourth power. And we could continue that, make layer after layer of the triangle, and those are the coefficients for x plus y to the fifth power, 6th, 7th, 8th, and so on. So that's how we get the coefficients. But how do we get the u thirds and u squareds and v's, and how do we fill in those variables? That is also part of, it's just a pattern, an overall pattern. And let's see here, I'm just going to get some of this out of the way. Over here, and I'll at least show you how to do it for these two. Okay, so we're expanding, and this is the one we're going to work on in class. We'll have some homework on this. I have x plus y to the third power, and I know my coefficients are right here. 1, 3, 3, 1. Because this is a plus sign, every sign in here is going to be a plus. That's a plus 1, that's plus, plus, plus. Now we got to figure out the x's and y's. And here's how we start, and I like to do it, I'll do it one variable at a time. I'll switch over to red here. My first term is an x, and that's to the third power. So this is going to be x to the third with the first term, x squared with the second term, x to the first with this term, and we don't have to write the first power. So I can knock that off of there. And then we would have x to the 0. But do we have to write x to the 0? Because x to the 0 is what? 1. Anything to the 0 power is 1. So we can not write it there, but that's the pattern. X to the third, x squared, x to the first, x to the 0. And that's gone. And now we can sort of do it right to left backwards, you know, here my last term is y, and that's to the third power. So here is going to be y to the third. Here we'll have a y squared, y to the first that we don't have to write, and y to the 0, which we won't write at all. And there's our expansion. 1x to the third, and let's not write the 1, why not? X to the third plus 3 x squared y to the first plus 3x y squared plus 1 y to the third. There's our expansion of x plus y to the third power. All right, and I'm sure you've seen the pattern, but let's do another one with the x plus y to the fourth power. So here are the coefficients: 1, 4, 6, 4, 1. And I should note here, if that was a minus in there, I said this was x plus y, so all the signs were plus. If this happened to have been a minus, you just follow a similar pattern. The first one here is going to be a plus, and then they just alternate. Plus, minus, plus, minus. Okay, here for the fourth power, again, we got the coefficients set up here. This is a plus, so everything's going to be a positive. And my leading variable is x, my power is fourth, so it's going to be x to the fourth, and then x to the third, x squared, x to the first, and x to the 0, again, which we will not write because anything with the 0 power is 1. And now I reverse. I have my y as my second variable, y to the fourth power goes at the very end, and then we start working back to the left. Y to the third, y squared, y to the first, y to the 0. You know, as we read this entire thing left to right, the x's powers decrease, the y's power increase. Here's our y to the 0, y to the first, y squared, y to the third, y to the fourth. And there's the expansion of x plus y to the fourth power. Again, you can continue like that forever with Pascal's triangle to get your coefficients, and then your x's and y's just follow that pattern. Okay, now let's try to apply this in some examples. And you know, here we're going to have maybe an x plus 2 or an x minus 5. One of those will usually be a number and not a variable, and we'll see how to apply that. So in example 7 here, we got the cube of a binomial, 3x plus 2, and that quantity is to the third power. And it's a plus. We're adding those terms in the binomial. So I know everything here is going to be a positive. That's going to be a 1, a 3, a 3, and a 1. And actually, let me spread that out a little bit more. I got plenty of room here. 1, 3, 3, 1. So this is my first term, and this is my second term. And these are all positives. So here my first term is 3x. So I'm going to have a 3x to the third power. Here I'm going to have a 3x squared. Here I'm going to have a 3x to the first, and then there would be a 3x to the 0, and we don't write it because that would equal 1. Now I'll switch over to red. Here is my second term, 2. And this is to the third power. So here I'm going to have a 2 to the third power. Here I will have a 2 squared. Here is 2 to the first, and here would be 2 to the 0, which is 1, so it's not going to change what we already have here. All right, now we got some stuff to combine in each term. Here's our first term, 3x quantity to the third. Well, 3 to the third is 27, and then we'll have our x to the third. Let's see what we have here. Our 3x squared is going to be a 3 squared is 9, and then x squared. And now we have this 3 times 2. Well, 3 times 2 is 6, times 9 is 54, plus 54 x squared. Plus. Now our 3x is to the first power, so we can multiply the coefficients. 2 squared is 4, 4 times 3 is 12, 3 times 12 is 36, 36x. And then at the end we have 1 times 2 to the third, 2 to the third is 8. And that should be our correct answer. Let me verify that here in the book. 27x to the third, 54x squared, plus 36x plus 8. There we go. There's our expansion of the binomial cubed. And that was a tricky one, because that 3 in there, you know, always treat that term as a quantity, put it in parentheses like I did here. And remember, you have to distribute that exponent. I think example 8 is actually a little bit easier. Yeah, example 8 we should have led with this one, because now it's just a simple x minus 1 to the third power. Again, coefficients 1, 3, 3, 1. Because this is a minus now, we'll start with a plus and then alternate. Negative, positive, negative. Our first term is x, and it's to the third power. So x to the third, x to the second, x to the first, x to the 0. Don't even put it in there. Now for the 1. Oh, that'll be nice. 1 to any power is just 1. So here we're going to have 1 to the third, 1 to the third, 1 squared, 1 to the first, 1 to the 0, which is 1. So actually, that's not going to change any of our coefficients at all. So here we just have plus 1 x to the third or x to the third. Here we have 1 squared is 1 times our 3 doesn't change it at all. It's just minus 3x squared. And then we have 1 squared is 1 times x to the first is just x, and we have our 3, it's just plus 3x. And then minus 1 to the third is 1 times 1 is 1. And there's our expansion of x minus 1 to the third power. A lot of math is just recognizing patterns. Now here's a little application, and this is kind of a lead into some stuff we do in calculus. We're finding the volume of a box. We got an open box, and it's made by cutting squares from the corners of a piece of metal that is 16 by 20. So the sides of this sheet of metal are set in stone. This is 16 inches, this is 20 inches. What changes is the size of these corners we cut out. This side is going to be x. It's a square, so this side will also be x. We're going to cut these squares out, and then we're going to fold up. You know, this will be the left side of the box. This will be the right side. This will be sort of the other side of the box, and this will be the bottom of the box. And then we're going to find the volume of the box when we cut out different size corners. So first we need to come up with a polynomial that will describe the volume of the box. Volume equals length times width times height. So this side of the box is 20 in length. But remember, as we change our value of x, we're going to cut this out, and we're going to cut this out. So how can I represent this piece, and I'll use red to highlight it, how can I represent the length of this side in terms of x? Well, if this whole side is 20, and we're cutting this off this side, and this off this side, our length here is going to be 20 minus 2x. This x we cut off, this x we cut off. Those are 2x's if we add them up. The whole side was 20. 20 minus 2x is this red side. And we cut the same length, x here and x here, and this whole side was 16. So how long is this red side? Well, the whole side is 16. We cut a couple x's out, so it's 16 minus 2x. So we want to represent the volume of the box, length times width times height. So volume equals, well, let's call this the length. How long is this side? You know, again, that's just going to be here in red, written in terms of x. That side is 20 minus 2x. This side here, the width of the box. How wide is it? Again, just the red side, 16 minus 2x. And then the height. Remember, when we chop these corners out, we're going to fold that up. So this dotted line will be the inside, edges of the box. And when we fold those sides up, the height of the box is that x there. So if we multiply that all out, we will get the a polynomial representing the volume of the box. And how I would approach this, I would FOIL this out. I would FOIL those together and get combined like terms, and then I would distribute the x across. And if we do all that number crunching there and collect our like terms, you're going to get a 320x minus 72x squared. And then a plus 4x to the third. So that's our polynomial that represents the volume of the box for different x's that we chop out. And what they asked us to do is find the volume when x is 1, find the volume when x is 2, and then find it again when x is 3. Well, the volume, if we plug a 1 in for x, we'd have 320 times 1 minus 72 times 1 squared plus 4 times 1 to the third. And we crunch all those numbers, and we get a 252 cubic inches, inches to the third power. So if we make the box 1 inch high, we're going to have that as our volume. We try crunching that number again with a 2 in there. Plug in a 2 for x. That would be a 2 squared. That would be a 2 to the third. We compute the volume, and you'd get a 384 inches cubed. So if we cut out a 2-inch square instead and fold those sides up, we get a box containing more volume. And we could also do it for 3. Cut that out as a 3. That will make these sides shorter. The length and width will be shorter, but the height is now 3 instead of 2 or 1. So we plug a 3 in for x, and we compute that, and we get 420 inches to the third. So bigger numbers of x produce more and more volume, but eventually that's not going to happen. Eventually this side of the box will get so short, the length and width will be very short and slim, and the height will be very high. Eventually those numbers will start going down again. So the tie into calculus here is you want to create a box that has maximum volume, as much volume as possible. You know that by cutting out 1, 2, and 3 in squares, you create boxes whose volumes are these numbers getting bigger and bigger. What are the possible values of x that make sense in the problem? This whole side is 20. What if we chose x as 10? If I cut a 10-inch off this side, and if this x is also 10, if I cut 10-inch off this side, we have no more left for the width or the length of the box. Same over here. I could cut out, if I cut out x as 8, this 8 cut out plus this 8 cut out would cover the whole 16. So there are some x's that do not make sense. So what values of x's make sense in the problem? We can write it as an interval. Oops. We want this side, this x has to be less than 8. This x has to be less than 10. So those would be some numbers to think about on there. Try several values of x to find the squares that should be cut to produce the maximum volume. You can solve this problem by trial and error, just plugging in different values of x. In calculus, we will apply calculus mathematics to this problem, and through the beauty of calculus, we will find the exact value of x that would maximize the volume of that box. Just something to think about over the summer before you take calc next year. All right, a couple problems to try for practice. Team huddle. Here we have a simpler one, x plus 2 quantity to the third. And here's a little more complicated one. Here you're going to grab a calculator probably when you're squaring that x and cubing that x. You're going to get some big coefficients for 72. And I'd also like to note right here before I forget, I added this. So these homework problems are not on your assignment sheet that I gave you at the beginning of the school year. So make sure you write these down. Maybe even find some room, squeeze them in on that assignment sheet. Page 30, it's only 4 problems, 72 to 75. And they're all cubing a binomial. So good spot. Pause the video, try the practice problems, and then fire it back up and see if you got the correct answers. Alrighty, let's see here. I'm probably going to need as much room as possible. I'm going to move this one up here, get this one out of the way for now. I'm not going to need that. So we have our x plus 2 to the third, using the variables that they give us here, u's and v's. Our first thing is a u, our second thing is a v, and it's a plus, so everything's a positive. We're going to have a plus 1, a plus 3, a plus 3, and a plus 1. So first, I'll do my first variable, and that's x, and it's to the third power. So x to the third, x to the second, x to the first, x to the 0, which I'm not going to write. And then my second thing here, my v is now a number, and that's going to be 2 to the third. So 2 to the third, and actually I'll switch over here to blue. 2 to the third power, 2 to the second power, 2 to the first power, 2 to the 0 power. And all that's left to do is, clean it up a little bit. 1x to the third is x to the third. Plus. Here we have 2 to the first, that's 2 times 3 is 6, 6x squared. Plus. 2 squared is 4, 4 times 3 is 12, 12x to the first. And then our plus 1 times 2 to the third is 8. And there's our answer. X plus 2 to the third power foiled out, or expanded, is right there. All right, 72 is going to be a little trickier because we're going to have some bigger numbers in there, but the idea is the same. Okay, number 72 here is going to be a little different, and I see one big difference is we don't have our x in the first term. It's just a 5, and then we have our minus 8x. So the variable's over here, and that doesn't matter. You know, we just follow that pattern that we've been learning. And this is a minus 5 minus 8x, so we are going to have some differing signs here. First, I'll set up my coefficients, 1, 3, 3, 1. And I plug in my signs. I'm going to start with a positive, and then we'll go negative, positive, negative. I'll switch over to red here. Now this is our first term in the binomial. It's on the left, so I'm going to start here with 5 to the third power, and then work my way down. 5 squared, and 5 to the first, and then it would be 5 to the 0, which we don't have to write. And now we have this as a quantity, and I like to write that in parentheses. That's 8x in parentheses, and we're going to start here with the third power and work our way left. So this is going to be 8x, that quantity to the third, and here we'll have 8x quantity squared, and then 8x to the first power, and then 8x to the 0 power, which we don't have to write. So let's start working on our coefficients here. This, we don't have any variables. 5 to the third is 125, and that would be times 1, so 125. And then we're going to have a minus. This will be our x term, and let's look at our coefficients. This was to the first power, so we can just ignore the parentheses. 8 times 5 squared. Yeah, that's a 5 squared. So that's going to be 3 times 25 times 8. 3 times 25 times 8 equals 600. 600 is our coefficient. X is the variable. Plus. Now here, you know, we got to worry about 8x squared is 8x times 8x, or 64x squared. So we're going to have 3 times 5 times 64. 3 times 5 times 64 equals 960. 960 x squareds. And then minus, here we're going to have 8x, that quantity to the third. So 8x times 8x times 8x. Well, for the coefficients, 8 times 8 times 8 is 512 x to the third. And there is our expansion of our binomial to the third power. Let's see, you know, usually you see things written highest power first, especially if you did do this on the TI-89 calculator. You would see negative 512x to the third first, plus 960x squared, minus 600x, and then plus 125. And there it is, some pretty big coefficients there. So be careful on the homework. Again, that homework's not on the assignment sheet. 4 problems on page 30.